Well, hello there, and it's so good to be with you again. We are going to continue our exciting journey in the realm of integral calculus, where we're having a ball together, and today we're going to look specifically at areas under curves, and it's going to be so much fun. So, without any further ado, let us get started. What have we got here? Goodness. We've got a graph. And it looks like a linear graph, no less. We've got to find the area. Now, I want you to take particular note of that word, area, okay? Because areas can't be negative, okay? Have you ever bought a negative block of land? Well, I don't think I have, otherwise I'd want my money back, wouldn't you? Well, that's what I mean. The area just means the amount of land, the amount of area in the block without considering a signed area, which is what an integral is. Okay, so we have to make sure that when we use integrals to get the areas, the signed areas, that we don't go getting negative integrals. That's what the game is with this particular topic, guys. Okay, I will explain. Okay, we've got to find the area of the region between the x-axis, the line y equals x plus 1, and the lines x equals 2 and x equals 4. And we have to check the answer out by working the area of a trapezium out. Well, good gracious me, that'll be fun. So, we're looking at that yellow area, guys. That's what we're looking for. But we have to see that the integral is going to be positive, or we have to make sure it's positive if it isn't, because if we get a negative result, then that doesn't mean we're talking about an area, it means we're talking about a signed integral kind of area, which we don't want. We just want the area. Oh, goodness. Now, what I've done there for you is I've drawn a little rectangle. Never forget that integrals are the sum of many of those little blue or whatever colour rectangles under the curve, under the line, under the function, right? And we've got to work out what our signed width and height are going to be, okay? Now I'm going to go that away for the x direction, so that means I'm moving in the positive direction. I'm going to go from x is 2 up to x is 4 in the positive direction. Good. So my delta x is going to be positive, okay? Now we've got that out of the road. Now, have a look at our y now. I'm going to go up that away, vertically upwards, going higher from a low point to a high point, and that means that my y is going to be positive, isn't it? Of course it is. So therefore, what will my signed area be, okay? The area is y times delta x of that rectangle, and indeed all the rectangles which make up that area, the total area, and that's a plus by a plus, isn't it? Isn't it? And what's a plus by a plus give you? Yes, it gives you a positive answer. So I can relax because my integral, if done the way that I'm saying I'm going to do it, with the terminals going from x terminals going from 2 up to 4, I'm going to be fine. I'm going to get a positive answer. So that will be the same as an area. Double tick for me. Love those ticks. Now, the area cannot be negative. We haven't got a negative area. I just wanted to emphasise the point. Okay, so you won't fall into that trap. And we've got, yes, the integral from 2 to 4 of x plus 1 with respect to x is positive. So we're laughing. Okay, yes, double tick. So let's do the anti-diff, and you get a half of x squared plus x, and no c's in sight. We don't need to do c because we're doing a definite integral from 2 to 4. Now what you do now is you work out the whole thing with 4 subbed in, like that, and you subtract the whole thing with 2 subbed in, and that will get you exactly that yellow shaded area. Ain't that exciting? Yes! Now, there's no tricks in that. Okay, 4 squared is 16, and half of that is 8, and plus 4 in the first bracket, and then the same thing, same process in the second bracket, no problem. So what did I get? I got 12 minus 4, which gets me 8 square units of area, okay? That's it. And I'm not going to say plus 8 square units, because that would kind of indicate that I was putting a sign on it. I just don't want it to be negative. It's a number, okay? There it is. Okay, that's it. Oh, yes, I've got to do the trapezium. I was starting to relax there. The trapezium thingy, okay? Now, I've got to check it, because you can do this one geometrically, okay? Not all of them you can do that with, but this one you can. So the area of a trapezium, do you remember? Well, it's the average length of the parallel sides times the perpendicular height, yeah? Okay, so that's going to be f of 2, that's one side, plus f of 4, which is the long side, over 2, added up and divided by 2. Then we're multiplying that by the vertical height, which in this case is an x, quote-unquote, height, if you like. But it's 2 units, isn't it, yeah? Oh, Mr. Snail, how are you this evening? Wow, it's been raining, so Mr. Snail, it would be a very, very happy little slitherer, I would say. Okay, Mr. Snail, thank you again. Now, where are we at now, guys? Yes, I'm just putting the numbers in now, guys, okay? So it's x plus 1's the function, so I'm putting 2 plus 1 in for the first term, 4 plus 1 in for the second term, adding them all up, dividing by 2, and then multiplying by 2. And we get 8 square units, and I'm about as happy as Mr. Snail now, because I got the same answer as I did for the algebraic technique. So I'm laughing too. Thank you, Mr. Snail. And we've turned the page. We've got another one now. We've got to find the area under the line of y equals x plus 1 between x is minus 2 and x is minus 4. So don't pay any attention to that red note thing. That just tends to confuse us. We're going from x is minus 2 to x is minus 4, which I think you'll take note of. That is a negative x direction, right? So what's their game, do you think? Why do they want us to go in the negative direction? Well, you'll see. It's actually pretty darn sneaky that they did that, and I'll show you why. Let's do a graph. Here's my graph. Look at that. What a wonderful graph, even if I do say so myself. Let's put some more stuff on it. Intercepts, an endpoint, and let's see what else we can do. Yes, that's the area. Now, that is the area they're asking us for, right? Between x is minus 2 and x is minus 4. But you note they want an area, so you have to be jolly careful that our integral expression doesn't come out negative. That's the game, all right? Right, there's my little rectangle. Always think about rectangles when you're doing these things, and you won't go wrong, okay? Now, we're saying from x is minus 2 to x is minus 4, so we're going to go in the negative x direction, aren't we? Yes? So all of our widths are going to be negative, aren't they? Negative, because we're moving in the negative direction. Okay, what about our heights? Oh, we're moving from the x-axis downwards to the y value of the function, and therefore we're getting a negative direction for y, and therefore our y's, compared to the baseline where x equals 0, will be negative, yes? So the plot thickens, doesn't it? So therefore, what about y times delta x? In other words, the signed area of my rectangle. What do you think? I know what I think, and I think it's mighty good, because it's going to be a negative times a negative, and what does that get us? It gets us a... Bah! It does not. It gets us a positive. Oh, goodness. I think someone's trying to trick me, and I think it was probably me. So it's a positive, guys, isn't it? Not a negative, and I'm a silly goat. All right, so just go with that, a positive. No, someone's playing tricks on me. It's a positive, not a negative. Oh, goodness gracious me. I don't know what happened there. Right, let's recover from that shock and get the area under the line, and it's basically x plus 1 integral of from minus 2 starting to minus 4 finishing with respect to x, and we don't have to do any argy-bargy to make it positive because it already is, because both the widths and the heights were negative. Okay, off we go. Let's do some integration throughout the nation, and what do we get? Very nice. Very nice. Do you agree? Good. Now we're going to sub in the whole thing with a -4. There we go. And then we're going to minus everything subbed in with a -2. There you go. Now we better clean it up a bit. What's that? Oh, that cleaned up well, didn't it? Goodness. Now you have a quick look at all that and see whether you agree with me. Yes, it looks good to me. Okay, so what does that come to? Oh, that's 0. That's nice. That second term. And we got 8 minus 4, which is 4 square units of area. Okay? Okay. That's really good, isn't it? Yeah? Oh, Mr. Snail. Do you want to say something to us? Oh, I think he does. What does he want to say? Oh, let us do some more. Ha, 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 Mr. Snail. Because you see, guys, if you're a vegetable gardener like me, you'd know that snails love lettuce, you see. Mr. Snail, get your mind off your stomach and back onto maths. Actually, he's a very mathematical snail. Did you know that? That's why he's part of our presentations. Look at the incredibly mathematical spiral he's got on his back. He's very proud of that. So thank you for your very, very nice little contribution, Mr. Snail, and please leave my lettuces alone. Okay, next page. Find the exact area of the regions enclosed by the graph of that thing. Now that you see the word area, area means be careful, not just integral. You might have to do some argy-bargy to get the integral to come out positive, right? So that's yes, I think we need a graph, don't we? Well, fancy that, the graph just appeared before our eyes just when we needed it. I can see a problem, guys. I can see a problem with that first area because I've done a few of these and I can see we'll have to do some argy-bargying on the big one under where the graph goes under the x-axis, but not with the one that's going from 2 to 3 above the x-axis. I will explain, okay, and you will see why. We're going to go in the positive x direction, and that makes all of our well, we better split this up into 2 regions, actually. Look, there's area 1 and there's area 2, and there's my rectangle in area 1 and there's my rectangle in area 2. Now, for both of those, my delta x's are going to be positive, aren't they? Because I'm moving in the positive direction. Oh, but for that one, y is negative because I'm moving in the negative direction to get to the point on the curve, aren't I? At the top of at the left-hand bottom corner, in that case, of that rectangle, yeah? What about, okay, so it's y equals delta, y times delta x. I mean, the area will be a negative times a positive for that particular region, which comes out negative. So I need to argy-bargy that one to get a positive value for area, yes? Or at least not a negative value for area, yeah? Okay, what about the other region? Yes, delta x is positive, and y, of course, is going upwards to get to the curve, yes, for that rectangle. So I've got a positive times a positive for y delta x, which comes out plus, which is very nice. So that one doesn't need to be argy-bargied at all, but the first one does, okay? Yes, what I'm saying is that integral would be negative from 0 to 2 in the positive x direction, and that one there is going to be positive from 2 to 3. So, yes, let's go for it now. We'll fix it up. Now, well, what I've done, the area required, what have I said there? What I'm saying is there, the first one, the first region, see what I've done to the terminals? I fixed them up, didn't I, properly? I reversed them, and that means that it turns the whole integral expression around to be the negative of what it was. So if it was already negative, which it was, turning the terminals around that way means in effect we're moving from 2 back to 0 along the x direction, which means that the widths will be now negative, and a negative width times a negative height gets us a positive. You like that? It's very, very nice, isn't it? And that's the second one. we've got that one doesn't need to be argy-bargied with, okay? That's just as is. Okay, let's just... Oh yes, we need to work out what this rather gruesome looking expression is before we try to integrate it, because I don't like my chances in the present form. So let's just do that. And we get that thing there. Oh yeah, I multiplied the second and the third linear factor out, right? And now I'm going to clean it up. Good, and now I'm going to multiply the whole thing by x. Okay, so that's what that cubic expression is when you've got rid of all the brackets. Okay, so now we can integrate to our heart's content. There it is, that's the first term, and that's the second term. First term being for the first region, argy-bargied with to make it plus, and the second term coming from the second region untouched, right? Okay, now we just got to go through the algebra soup. Okay, now what I've done there is I've integrated, so you see if you agree. Yes, I get it. Yes, I get it. Yes, I get it. Everything's good, okay? But now we've got to go through the algebra and not get ourselves messed up, because I think it's a bit soupy coming on. This is a very important thing to remember. When you get to this point, lots and lots of things can go wrong. You're doing a lot of mental processing, and you've got to be very careful not to mess it up. So to just go slowly, slowly, slowly. Doesn't matter how many times or how many lines you take. Just keep your head and don't do too much at once, because that's when you come unstuck. Okay, so what have I got there? I've got, okay, two bracketed terms. The first bracketed term is from the first integral. The second bracketed term is from the second integral, okay? But there's lots of work to do to get the answer. Right, the first one, what on earth is that? Okay, that 0 comes from the first bracketed term with 0 subbed in, then subtracting the second bracketed term is there is when you sub 2 in, okay? So that's coming from the first bracketed term in the line above, yeah? Now we'll deal with the second bracketed term. That's with 3 subbed in, and now with 2 subbed in. Now, look at all that. Look at all that algebra soup. Please be careful and don't do too much, okay? That's where you come unstuck, as I said. Right, so that's going to be 0 minus 2 times, goodness, what is all that? What I've done is I've just multiplied those 2's out, and I've done some basic cancelling and simplifying where appropriate. And then the second, okay, that's the first term was a 0. That's what I've some basic cancelling and fixing up from that second term, which is bracketed. And then I've got the, what have I got then? I've got, oh yeah, okay, that next bracketed term, you can see in the red box, is from the third term, where I've got all the 3's subbed in. That's what that comes to. And then the next term, oh, what have I done there? Yeah, that looks right. That looks right. That looks right. I'm just getting myself all messed up here. It looks okay. I'm just trying to work out what I did. Oh, I see what I did. Take a step back. Take a step back. Look, I'm going to watch you. Watch how clever this is. I'm going to reverse this. Look. Ooh, look at that. So therefore, what I've done, guys, I've just worked it out. Sorry for the rambling. The 0 term is from the first 0 in the algebra soup at the bottom of the page. The second term, I've noted that in the line previous, the equal sign in the line of previous, we've got 2 identical terms where they've got the 2's cubed. That's the second and the fourth term in that expression at the bottom of the page are the same thing. So I've just doubled them, okay? That's what I did. And then the next term is from where all the 3's were subbed in, if you get what I'm saying. Now we're right again. Let's go. Oh dear. Okay, so that comes to all that. I've simplified again, and that comes to all that. I mean, it's algebra soupy, isn't it? Absolutely soup everywhere. So, as long as you don't get it, egg on your face and fall in the mud. You know what I mean? So that comes to that. And I had to LCM that with a 12 and to fix that all up. And when you finally get there, you've got the right answer, hopefully, which is 37 over 12. And that's what it is. That is the right answer. Wow. But look, please take my point of being very careful when you get into the algebra soup. It's where a lot of students go wrong. A lot of students go wrong. Okay, that was that. All right, happy to leave that. Goodbye, Mr. Algebra Soup. Now we've got another one. This is this an area one? Yes, it's an area. Same problem as before, guys. The left-hand region is going to come out as a negative integral if we move in the positive x direction, as you will see. And the right-hand term will be okay, but that's why we have to be careful with it. So let's move in the positive x direction. Yes, and let's work out our rectangle situation. Okay, so there's my two rectangles. Good. This one is a negative y because we're moving in the negative direction. That one is a positive y because we're moving in the positive y direction. Okay, so both delta x's or widths are positive because that's the way I organised it. And that area there is going to be a negative times a positive, which comes out negative. So that's an argy-bargy one for us. And the next one is a positive times a positive, I think, for the area. Yes, and that's a positive one. So no problem with that one. But we have to get argy-bargy the first one. Okay? And if you don't do those rectangles, guys, when you're at this formative stage of your doing this stuff, well, I don't know how you're going to go, but I don't think it'll be too good, to be perfectly honest. So please do them. Right. Sorry for the rant. The area is going to be, yes, what I've done there is I've negatived the first one, okay, to make sure it comes out positive. Yes, there it is, and I've just I've done the second one, and now I haven't changed anything, okay. And now look what I did there in that line there. I decided I wasn't too keen on the negative, so I just reversed the terminals. Ain't that clever? They're the two ways that you've got to argy-bargy them, guys. Okay, they're the two options. So I thought I'd show you. And that's the second bit. Now we just have to go through all the algebra stuff. That's the anti-diff. Agree? Yes, it is. Okay, and that's the anti-diff of the second term. Same anti-diff, different terminals. All right. Now, usually you use square brackets for these anti-diff expressions for definite integrals. It's just kind of convention. Okay? So what do we get from that? I've subbed in the numbers, and that's from the first square bracketed term, and this stuff is coming up from the second square bracketed term. Again, there's plenty of scope to go wrong here, so be careful, please. Yes, that's the first term. And what I've noticed is that there's two identical terms there. The second and fourth term are the same. So I'm just minusing 2 times that term. And here comes the last term. Now we can do our major fixing up and simplifying now. So that's going to be minus 11 over 3 for the first bracketed term. And that's going to be minus 2 times minus 16 over 3. Because 3 8s are 24, and 8 minus 24 is minus 16 over 3 for that term. Next one's going to be, I put everything over 3. So 3 16s are 48, and 64 minus 48 is 16 over 3. Now we can just do a bit of minor cleaning up. We get that now. I think we can give it the knockout punch now. That's going to be 32 and 16 are 48 from the second and third term. Take away 11 gets us 48 minus 11 over 3, which is 37 over 3 square units. And Mr. Box is champing at the bit. Thank you, Mr. Box. You're a good man. And that was it, guys. We did it. You see? No problem. Oh, yes, we're very, very thrilled because we did it and we know exactly how to do it. So, how do you feel? Pretty good, I hope. And I'm feeling very happy too. So thank you, everybody, and have some practice, have some fun, and we'll see you next time. Okay, bye.